Welcome to Lecture 30, the last lecture of Unit 8, Gravitation. As I promised, we're going to go through one last example, and that has to do with a pendulum. So a pendulum is a way that we can actually measure little g here on Earth or on other planets. But first we need to derive an expression in order to do so. We're going to take a little bit of a hand-wavy approach here and use dimensional analysis. So this is not a rigorous derivation. However, it will serve enough to justify the expression that we come up with. So first of all, in this process, we want to understand what units we're going to need in order to describe the pendulum's period. So a period is a period of time, and so what we really want is something that turns out to be, for SI units, in seconds. Now, knowing that though, there's a lot going on with gravitation, and what kind of physical quantities might be possible to be involved when we're looking at the motion of the pendulum. Gravitation seems to have a lot to do with mass, so all of these choices have mass here as a possibility. How long or short the pendulum is seems to stand to reason as well. The volume of the pendulum doesn't seem to be maybe as important, but this acceleration rate, well, that's what we're actually looking for. So it's possible that any of these three things could be involved in whatever expression we are attempting to derive. However, of those three things, one of them cannot be combined with the other two in order to end up with units of time, right? Length and acceleration, both of those have meters somehow involved, and maybe we can get some cancellation going to get to the seconds that are in acceleration, but we can't cancel with kilograms. So mass, maybe it doesn't actually need to appear in my expression. So if this is correct, how will the dimensional analysis go? How could I combine little g and length in order to get me some sort of period of time? Well, a time period in seconds is going to have to require something like the square root of a meter over a meter per second squared, right? Because we want these meters to cancel. Seconds we want in the numerator, and we just want 1 second, not seconds squared. So that's telling me that it stands to reason that the time period should be proportional to the square root of the length of the pendulum divided by g. And as it turns out, this is almost enough to give us the expression we need. But one thing you have to bear in mind is that whenever we are doing dimensional analysis, we're not able to produce necessarily an exact relationship. We may be able to produce a proportionality, but we do not know for sure if there's not some constant that precedes that, right? So when we talked about Kepler's laws, we knew that the period of the orbit would be proportional. Period of the orbit squared would be proportional to the semi-major axis cubed, but we didn't know what that constant or proportionality was. Okay. However, in this case, again, we don't really know if there's some sort of constant involved. So I will save you the nitty-gritty of how you could derive the exact expression. It turns out that it is proportional to square root of L over G. And that constant of proportionality that precedes it is simply a 2 pi. Okay, so this is actually enough to tell us what the period is for a simple pendulum. And yet, that doesn't seem to be sensible. Why would the mass of the pendulum not actually matter? It seems a little counterintuitive. But we can actually test this out and in the process effectively measure g to see if it's correct. Because in this expression, t equal 2 pi times square root of L over G. If I plug in 9.8 here, and let's keep it simple and make my pendulum a length of 1 meter, then I should find, if all of this is true, that the time period is 2 seconds independent of the mass. So I can do this experiment with a certain mass on the end of my 1 meter pendulum, and then I can repeat it using a larger mass or a smaller mass and see if I still get 2 seconds. So if we were doing this in a normal classroom, I would have a demo at this point in which we would actually time this with a timing gate, and we would use different masses to demonstrate this, and I would actually ask you to help me collect data. But you can refer to the data that was collected the last time that I taught this class. It's accessible here on this Google spreadsheet, and when you look through the data, you do see a lot of students reporting a period of 2 seconds, which means that the little g of 9.8 is correct and measured to be what it's supposed to be. Moreover, the mass of the pendulum doesn't actually come into play. But what does come into play is the length of the pendulum and little g. And remember that little g depends on where you are. So this 2 second period of time is relevant only on Earth. What will happen if I place that same 1 meter pendulum on another planet? So let's take Mars, for example. Let's make a prediction before we actually calculate it. So if we have this equation here, and we know that Mars is smaller and has weaker gravity than the Earth, we are reducing the denominator here. Therefore, we should expect the period to increase. So let's see if that's the case. So I'm not told the exact value of g, but I know from an earlier expression that I can find it based upon knowing what the mass of Mars is and what its radius is. So what I can do is I can plug this expression into here for little g. So this is going to tell me that the time period should be 2 pi times the square root of L r squared over capital G times the mass of Mars. So what does that mean? On the mass, on the time period for Mars is going to be, if I take the values that are given in the problem, L times, it's half of the Earth's radius, but then that gets squared, right? So 0.25 times r squared. And then in the denominator, we have only 1/10 of the Earth's mass. Okay, so effectively we've got 0.25 over 0.1 in the numerator, and that's the only difference underneath the square root, and that's the only difference between this expression and this expression. So when I figure all that out and punch it into my calculator, it's telling me that this is going to be 1.58 times the mass, the time period of the pendulum on Earth. Okay, so in other words, the pendulum on Mars is going to take over 150% longer on its time period, 1.5 times longer for its time period than that 2 seconds that we had here on Earth. Now, let's say that I go to a world that is more massive and see what happens on Saturn. So we're going to take that same expression, only now for Saturn we are going to be plugging in 9 times the radius, which when I square that in the expression gives me 81 times the radius of the Earth squared, all over g times 95 times the mass. Okay, when I plug in the numbers there, that's going to tell me that Saturn is going to have a time period of its pendulum of only 92% the time period on Earth. So when I have a greater acceleration rate, it makes sense then that the time period of the pendulum would be shorter, so that it is being accelerated more and oscillating back and forth more quickly. Speaking of oscillations, although this concludes Unit 8, next lecture we will begin oscillations, and thinking about the periodicity of this simple pendulum is a good way to start thinking about what it means for something to oscillate. More on that in lecture 31.